Hi everyone. So in the last few videos, we've been focusing on different methods of integration. So we learned about substitution, and then we learned about integration by parts, and then different kinds of trigonometric integrals, and then we did trigonometric substitution. And so this is kind of our last main method for evaluating integrals. So we're going to be focusing on this method called partial fractions in this video as well as the next video. So the main idea behind partial fractions is that it's basically a method for taking a more complex fraction, or I should say a rational function. So when I'm saying fraction in this class, it's not just going to be a fraction of numbers, it's going to be a rational function, so a polynomial divided by a polynomial. So what we're going to do is learn a way to take a more complicated fraction and break it up into simpler fractions that are easier to integrate. So I want to start by actually kind of doing the reverse process. So I want to do as sort of a warm up just to remind you of the mechanics of, making a common denominator and adding together fractions. I want to just go through the process of adding two fractions together. So let's say that we wanted to add up 2 over x minus 1 plus negative 1 over x plus 2. So I'd encourage you to just, pause the video, do this yourself. Just make sure you remember how everything kind of plays out with making a common denominator. So how would we do this? Well, in this case, because the two denominators, they have no common factors. So we need to multiply each fraction by the denominator of the other over itself. So for the first fraction, that means we're multiplying by x plus 2 over x plus 2. And then for the second fraction, we're multiplying it by x minus 1 over x minus 1. Okay, so what's that going to give us? Well, for the first fraction, we're going to get 2x plus 4 over, and so now we have our new denominator of x minus 1 times x plus 2. And then our second fraction, so we have to make sure we multiply negative 1 with both parts of the numerator. So that's going to be negative x plus 1. And that's over x minus 1 times x plus 2. And so then we can add together our common, or now that we have the same denominator, we can add the numerators together. So we're going to get a total of 2x minus x, or sorry, let me just write it in order. So we have 2x plus 4 minus x plus 1, and we can multiply out this denominator now. So it's going to be x squared, and then we have plus 2x minus x, so that's plus x, and then minus 2. And so final answer here would be, we have 2x minus x, which is x, and then we have 4 plus 1 is 5. All right. So as I mentioned, basically what we're going to be doing in this video is doing what we just did now, but kind of backwards. So, here we started with two fractions, we added them together by making a common denominator, and we ended up with this. So in this video, we're going to be starting with something that looks more like this bottom answer and learning how to split it up into the two pieces above. So let me just write that down. So in this video, we will be learning how to reverse this process. So why would we want to do that? Like, why is that a useful thing? So why is this useful? Well, let's say that we were trying to integrate this fraction that we have at the end here. So let's say we were trying to take the integral of x plus 5 over x squared plus x minus 2. So we actually don't have any methods yet that will work for integrating this. You might think of splitting it up a different way. So like you could split this into two fractions, like x over x squared plus x minus 2, and then 5 over x squared plus x minus 2. And that's a method that will work in some types of fractions, but it's not really going to help us here. Like if you try to integrate either of those two things, you'll get stuck again. So, that method of breaking up the fractions isn't going to work. So again, I just want to write this down here. We don't know how to integrate this. So if we can figure out how to break it down the way that we did above, so, we saw where this came from, right? We saw that x plus 5 over x squared plus x minus 2, it originally came from 2 over x minus 1 plus negative 1 over x plus 2. So if we break this down now into two integrals, so let's actually pull also the constants out. So we have 2 over the integral of 1 over x minus 1 dx, and then we have minus 1 times the integral of 1 over x plus 2 dx. These are actually much easier to integrate. So these are just going to both be ln. So you could do a substitution here, but this is a case where I think substitution is just going to kind of slow you down and it's not super necessary. So if you wanted to do substitution, you could say u is equal to x minus 1. But du would just be equal to dx. So it's one of those substitutions where you wouldn't really end up changing the integrand much, right? You would just be replacing x minus 1 with u. So you're welcome to do a u substitution, but I just want to kind of point this out as one where, I think especially as we do more of these, you should be able to just kind of recognize that, okay, well, because it's 1 over x minus 1, that's going to be ln of absolute value of x minus 1. Right? Because typically when if you have something like ln of something that's not just x, you have to use the chain rule. But the chain rule, the derivative of x minus 1 is just 1. So basically that's why this antiderivative works the way it does and why you don't really have to do a substitution. And then similarly here, we have ln of absolute value of x plus 2. And so these are what the answers are going to kind of come out looking like for the most part with the types of problems we're doing today. We'll see a lot of ln. So maybe let me just make a quick note of that. So note the antiderivative of 1 over, and I'll make this a little bit more general. So let's say we have ax plus b dx. So what is it going to be? Well, we can start by saying ln of absolute value of ax plus b. But depending on what this number a is, so if this number a is just 1, which it was in these two cases, right? In these cases, we just had x, then that's it. But if this number, like let's say that this had been instead 2x minus 1, well, then we would have to multiply by a half to get rid of that extra 2 that would come out by using the chain rule. So in general, you would do 1 over a, whatever that leading coefficient is, times ln of absolute value of ax plus b. So this is going to be an important fact to be aware of. You can always just use substitution, that's fine, but I think, again, it's kind of nice to be able to do this in your head a little more quickly. Okay, so I want to now look at how this process of reversing the, what we did here, how it works. We're going to get into some other examples later in the video, but I actually want to start with this same example. And, the reason I want to start with this example is I want to show you, we know, right? We know that this fraction can be broken into these two fractions. And that way, when we find our final answer from this, if it matches with these two original fractions we got, you'll be convinced that it works, right? Whereas with other examples, you just kind of have to believe that it's true. This one, we actually saw exactly where this fraction came from. So this process that we're going to be learning is what is called partial fractions, or sometimes it's called partial fraction decomposition, because basically we're taking a bigger thing and kind of breaking it down. And so that's where the decomposition idea comes from. Okay, so let's say again that we were starting with that end fraction that we got, right? X plus 5 over x squared plus x minus 2. So the first thing we want to do is we want to factor the denominator. So let's do that. So we already saw how this factors, but usually you might have to go from scratch. So this is going to factor as x plus 2 times x minus 1. So why do we factor the denominator? Well, that tells us, what are the two other fractions that this fraction could come from, right? It kind of tells us the other two denominators that could belong to the smaller fractions. And so our goal is to find two fractions that add up to this fraction. And so we're just going to kind of say, okay, let's suppose that there are two fractions. And so what I'm going to call those two fractions is, first one is going to have x plus 2 as a denominator, and I'm just going to put a letter a here. And that a is going to be like a placeholder for whatever, mystery numerator we're going to find. So we're basically here, we're kind of making an assumption. We're assuming that we can write this fraction as a sum of two smaller fractions. And then what we'll do is we'll go through the process of adding these two fractions together, and that will allow us to figure out what a and b have to be in order to make this true. So basically the next few steps are going to be very similar actually to what we did up here. It's just that now we're doing it, instead of with two specific numbers, we're going to do it with a and b. And then we'll see what we get as our numerator at the end of that, and that will allow us to figure out what a and b are. So first step would be to make a common denominator, right? Same way that we did with the other ones. So we're going to multiply each of these by what's missing. So this first one will be x minus 1 over x minus 1. And then the second one will be x plus 2 over x plus 2. Okay, so let's see what that gives us. So for the first fraction, we're going to get ax minus a, and then our new denominator is x minus 1 times x plus 2. And then for this second fraction, we're going to get bx plus 2b over x minus 1 times x plus 2. And so now if we put these two fractions together, we're going to get ax minus a plus bx plus 2b all over x minus 1 times x plus 2. So our goal is to find a and b. So maybe let me even write this down. So our goal is to find a and b such that this fraction is equivalent to our starting fraction, right? So our starting fraction was x plus 5 over x squared minus x plus 2, or minus 2. Plus x, sorry. I knew there was a plus somewhere. And so if we compare, the end fraction we have here and this fraction we have here, their denominators are the same, right? So if we want to ensure that this fraction at the bottom that we just came up with is equivalent to the one that we started with, really what we want to make sure is that this numerator must be the same as this numerator. So let's write that down. So we have x plus 5, or actually let me write the first one, or the second one first. So we have ax minus a plus bx plus 2b is supposed to equal to x plus 5. So the way that we're going to end up solving this, it's not going to be what you might think of as a typical method for solving an equation. So first thing I want to point out is that we're not solving this for x, right? We're not trying to figure out what x is. We're trying to figure out what a and b are. And the way we can do this is basically by just kind of comparing our left and right hand side. So for example, if we look at the left-hand side and we look at, what are the parts that contain x? So remember that a and b stand for numbers, right? And so the only parts that have an x in them are this and this. And so that means that this x on the right-hand side, if the left and the right-hand side are supposed to be equivalent to each other, the only way that you could possibly get this x on the right-hand side is by adding up whatever a is times x plus whatever b is times x. Because these two parts here, they don't have an x in them. So that x on the right-hand side must have come from this ax and this bx. And so what does that tell us? That tells us that these coefficients, a and b, together have to add up to 1, right? Because this x here is 1x, so whatever we have as our a and our b, together those need to add up to 1. And then similarly, if we look at the remaining portions, so negative a and 2b, those have to add up to 5, right? Because that's, this 5 comes from the part that's just numbers, the part that doesn't have the x's in it. So we have negative a plus 2b is equal to 5. And so from here, we're just solving a system of equations. So we're not solving for x, right? We're solving for a and b. And so you can kind of forget about x and just focus on these two equations. So there's a variety of methods for solving systems of equations. This is something you should have learned in like your Math 98, which is a North class, basically like a beginning algebra class. But to solve a system of equations, one method you can use that's kind of my preferred method is we can solve one of the equations for one of the variables. So for example, a is equal to 1 minus b. And then we can take that result and plug it into the second equation. So in the second equation, I'm going to replace a with 1 minus b. And so now we have an equation that only has b's in it, and we can actually solve it. So we have negative 1 plus b plus 2b is equal to 5. And so that tells us that 3b is equal to 6. And so that tells us that b is equal to 2. And so now if we go back to our top equation here, we said that a was equal to 1 minus b. And so that tells us that a is equal to 1 minus 2. So a is equal to negative 1. So what does that tell us? Let's remember what a and b represent. So a, remember, if we go back to the beginning, a represents the numerator of the fraction that has x plus 2 as its denominator, and b represents the numerator of the fraction that has x minus 1 as its denominator. So what does this end up telling us at the end of the day? It tells us that our original fraction, x plus 5 over x squared plus x minus 2, can be written as 2 over x minus 1. Actually, let me write it in order because I'll do a first. So a was negative 1, and that was the numerator of the fraction that had x plus 2 as its denominator. And then b was 2, and that was over x minus 1. And then, if this was a problem that we'd be doing in this class, typically the next thing you would want to do, you would be doing this because you were integrating. But we already saw what happens when you integrate this, right? Because they just break down into logarithms. Okay, so let's do another couple of examples. So we're going to do like 3 more examples. And the next one is going to be kind of similar to the one that we did, but just like a little bit trickier, more challenging. But then we'll also see some examples that bring up something new. So this next example, I want to use partial fraction decomposition to integrate the following. So we have x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. Okay, so our first step is to take this integrand, and we want to factor the denominator. So we can start by factoring out an x. So then we're left with 2x squared plus 3x minus 2. And then there's a lot of different methods for factoring, and you might have learned, there's like something called like the diamond method or the box method. Personally, I think that guess and check is really like the best method for factoring. What do I mean by guess and check? I basically just mean that if you take this thing here and you think about, where could this have come from? Well, you can see that it would have to be 2x and x, right? That's really the only way that we're going to get 2x squared. And then these second two numbers have to multiply to give you negative 2. And you don't have that many options, right? You can just try a few different things. We could try 2x plus 1 and x minus 2, for example. But if you multiplied this out, you would get 2x squared minus 4x plus 1x. So that wouldn't give you the right middle term. And so we actually want to switch this to being minus 1 and plus 2. Okay, so let's see. So we have x times 2x minus 1 times x plus 2. All right, so now we want to split this into, in this case, it's going to be 3 fractions. So our fractions are going to be, mystery number A over X, make that a little smaller, plus mystery number B over 2x minus 1, plus mystery number C over x plus 2. So our next step is to make a common denominator. So it's a little bit more complicated in this one because we have 3 factors in the denominator. So our first fraction, a over x, we have to multiply that one by basically just everything that's missing, right? So what's this one missing? It's missing a 2x minus 1 and an x plus 2. And then the next one is b over 2x minus 1. So what's this one missing? This one is missing an x and an x plus 2. And then finally the last one, x plus 2, or c over x plus 2, that one is missing an x and a 2x minus 1. Okay, so let's actually, I'm just going to write above here what these multiply together to be just so that we can go to the next step more easily. So if you multiply together these two things, we already saw that that gives you 2x squared plus 3x minus 2. If you multiply together x times x plus 2, that's going to be x squared plus 2x. And if you multiply together x times 2x minus 1, that's going to be 2x squared minus x. All right, so once we do that multiplication in the numerator for the first one, we'll get 2a x squared plus 3a x minus 2a over this new denominator. And then for the second one, we'll get bx squared plus 2bx over the new denominator. And then for the last one, we'll get 2 times c x squared minus cx. And that's divided by, again, that same new denominator. So x times 2x minus 1 times x plus 2. Okay, so I'm not going to write the next line out where we added these 3 together because we can basically see what's going to happen, right? We're just going to add these 3 numerators together over the denominator that they all have. So what do we want to do next as our kind of comparing, our new fraction to our original fraction? Well, the numerator of the new fraction is basically going to be all these 3 things added together. And what's the numerator of the original fraction? It was x squared plus 2x minus 1. So that's what we need to compare, left and right. So we're going to have all this stuff, 2ax squared plus 3ax minus 2a plus bx squared plus 2bx plus 2cx squared minus cx. So that must be the same as this original numerator of x squared minus, was it plus 2x? Yeah, plus 2x minus 1. So now we just want to do the same thing we did on the other one and kind of compare left and right hand side. So let's look at where the x squared comes from. So that x squared term comes from adding up 2ax squared plus bx squared plus 2cx squared. So altogether, those 3 things have to add up to give you x squared. And so that means that 2a plus b plus 2c, together, those must add up to 1, right? Because that's the coefficient of x squared. Then if we go through and look at the x's, so we have 3ax, 2bx, and negative cx, those have to add together to give you 2x. And so that tells us that 3a plus 2b minus c has to add up to 2. And then our last one, well, we just have this negative 2a. That's the only one that has a, that doesn't have an x in it, right? And so that tells us that negative 2a, maybe I'll write it over here, negative 2a has to equal negative 1. And so it's kind of nice when that happens because now we're going to immediately be able to figure out what a is, right? And that will make, otherwise this would be a little more complicated. We'd be solving 3 equations and 3 variables, but really we're pretty much just going to be back to a situation like the last one. Okay, so if we start off by saying, okay, we know that negative 2a is equal to negative 1, that tells us that a is equal to 1/2. And by the way, we'll see that we're going to get fractions basically for all of our values of a, b, and c in this, and that's okay. So it's going to kind of temporarily look complicated, but remember, if you go back to the first example we did, we ended up pulling out the numerators outside of the integral, so it doesn't really end up affecting much. It's just kind of a fraction that's just going to be there. All right, so now that we know that a is 1/2, we can go and put that value of a into both of the top 2 equations. So the first equation, if we put in that value of a, we're going to have 2 times 1/2 plus b plus 2c is equal to 1. And then that would simplify to being 1 plus b plus 2c is equal to 1. So let's take this equation and solve it for b, and then we'll plug that into our next equation and along with what we already know a is. So this would tell us that b plus 2c is equal to 0, or that b is equal to negative 2c. So now that we know that b is equal to negative 2c, now we can take this third equation and work with that. So the third equation says 3 times a, so a is 1/2, plus 2 times b, and we're plugging in for b, negative 2c, minus c is equal to 2. And so we're going to end up with 3/2 minus 4c minus c is equal to 2. And so that gives us negative 5c is equal to 2 minus 3/2. So what is 2 minus 3/2? Well, 2 would be 4/2, right? And so we're going to be left with 1/2. And so that tells us that c is equal to negative 1/10 if we divide both sides by negative 5. So now we know what c is, we know what a is, and now we can figure out what b is. So b is supposed to be equal to negative 2 times c. So if we take negative 2 times negative 1/10, that's going to simplify to give us 1/5. Okay, so now we know what a, b, and c are, and now we can go back to our fraction and break it down into those pieces and see how it integrates. So our original fraction, or our original integral, was the integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. So now we know that we can break this down into 3 different fractions. So let's remind ourselves, what all these numbers represent. So a was the coefficient, or was the numerator of this one, right, of x. So our first thing is going to be 1/2 over x. And then our next part was b, so b was 1/5. And if we look back, that was the numerator that goes with 2x minus 1. So we have 1/5 over 2x minus 1. And then our third one was negative 1/10 over, and so the remaining denominator was what was it, x plus 2. So now we can break this into 3 integrals, and as I mentioned earlier, even though we have these fractions, it's not really going to matter because we can just take each of them outside of the integral. So we're going to end up with 1/2 times the integral of 1 over x dx plus 1/5 times the integral of 1 over 2x minus 1 dx. And then we have minus 1/10 times the integral of 1 over x plus 2 dx. And so now we can break each of these down using the thing that we talked about on the previous page about logarithms, right? So the first one is just going to be ln of absolute value of x. Then the second one is going to be 1/5 times, so this is one of the ones where the leading coefficient is not 1. So what is the antiderivative of 1 over 2x minus 1? Well, it's almost ln of absolute value of 2x minus 1, but we need to compensate for that extra 2, and so we have to multiply this by 1/2. And then here we get minus 1/10 times ln of absolute value of x plus 2, because again, in that one, the leading coefficient is 1, and so we don't need to worry about any chain rule stuff going on. So as our final answer, we'll get 1/2 ln of absolute value of x plus 1/10 times ln of absolute value of 2x minus 1 minus 1/10 times ln of absolute value of x plus 2 plus c. Oops, that was a little crooked. Let me make that better. Okay, so as I mentioned, we're now going to see an example, actually 2 more examples that bring up something a little bit different. So the next example I want to look at is we're going to find the antiderivative of 5x minus 3 over x squared minus 2x plus 1. So let's start this the same way we started the other ones, right? So we're going to start by factoring the denominator. So we have 5x minus 3 over x squared minus 2x plus 1. That's going to be equal to 5x minus 3 over x minus 1 times x minus 1. So this is what's different about this one. So when you have a denominator that has a repeated factor, like this one. So let's think about, going way back to the beginning, why was it that we had, why was it that like the factors of the denominator were the denominators of the things we were adding up? Well, it's basically because, how can you get a denominator of x squared plus x minus 2? It was by multiplying these two together to make a common denominator, right? And so basically the only 2 different denominators that you could have that would, when you make a common denominator, give you this, would be the 2 factors of this thing that I circled. And so if we think about it here, we want to think about what are all the possible denominators that we could have that if you added those fractions together, you would get a denominator of x minus 1 times x minus 1. So one possibility would be x minus 1. And what's the other possibility? Well, we don't want to just say b over x minus 1, because then that would just, if you had 2 things that already had a denominator of x minus 1, then the common denominator would just be x minus 1, right? It wouldn't be x minus 1 times x minus 1. So the denominator of this second one is actually going to be x minus 1 squared. Because if you think about it, if you add 2 fractions together and one of them has a denominator of x minus 1 and the other one has a denominator of x minus 1 squared, what's the common denominator you're going to make? Well, it's going to be x minus 1 squared. So this is something that you have to recognize in the future. Anytime you have a repeated factor in your denominator, you need to not only include, one version of it, you need to do as many copies as you have. So if this had been, let's say that there was a third one here, then you would have to actually say plus c over x minus 1 cubed. So however many factors you have repeated, you need to include that many possible fractions that it could come from. We're probably not going to see more than 2, to be honest, but just so you know that if there were 3, you would do 3. If there were 4, you would do 4, and so on. Okay, so let's now do the same thing we did on the last one. So we're going to make a common denominator. And that's actually a little easier for this one because the only thing that needs to change is the first one, right? So we're going to multiply the first one by x minus 1 over x minus 1. The second one is still going to be b over x minus 1 squared. Okay, so when we add these two things together, we get ax minus a over x minus 1 squared plus b over x minus 1 squared. So now we can do this thing of comparing our numerators, right? So we know that when we add together these numerators, that we should get the same as the numerator that we started with. So we should find that ax minus a plus b should be equal to 5x minus 3. Okay, so what do we have for x's? Well, in this case, we only have ax. So this is one where we'll be able to kind of solve it a little bit more quickly. So we know that ax has to be equal to 5. Or sorry, let me say it differently. We know that ax has to be 5x, so we know that a is 5, right? Like the only x that we have is a times x, and so therefore a has to be 5. And then if we look at what's left, we have negative a plus b is supposed to equal negative 3. So since we already know that a is equal to 5, we can take this second equation and just plug that in. So we have negative 5 plus b is equal to negative 3, and that's going to tell us that b is equal to 2. So we now know that b is equal to 2 and a is equal to 5. So now we can put those in as our numerators. So our original integral again was 5x minus 3 over x squared minus 2x plus 1. And we just figured out that we can break that into two fractions. So 5 was the numerator of just the x minus 1 part. And then 2 was the numerator of the second part. So that's the x minus 1 squared. And then we can split this apart into two integrals. So we have 5 times the integral of 1 over x minus 1 dx. And then here we have 2 times the integral of 2 over x minus 1 squared. Oops, sorry. I pulled out the 2, so this should just be 1. So we know what the first one's going to give us, right? This is going to be 5 times ln of absolute value of x minus 1. For the second one, let's rewrite this as 2 times the integral of x minus 1 to the negative 2. So this is another example of one where you could do a substitution, but it's not really necessary because the substitution you would do would be u is equal to x minus 1, but then du would just be dx. So you wouldn't really be changing much about the integral. So you might as well just kind of do the power rule, but with x minus 1 as your input. So what is that going to give us? Well, we still have 5 times ln of absolute value of x minus 1. And then here we're going to have 2 times, so what will the new exponent be? Well, we just add 1 to negative 2, so that's negative 1. But then we have to multiply that by the reciprocal of negative 1, which is negative 1. So altogether, this is going to be equal to 5 times ln of absolute value of x minus 1 minus 2 over x minus 1 plus c, right? Because this becomes negative 2 and then negative 1 exponent puts it in the denominator. So that's one other kind of antiderivative that you'll just see coming up a lot with these types of problems that you should probably be aware of. So anytime you're taking the antiderivative of 1 over, let's again for generality, let's say ax plus b squared. What's that going to be? Well, it's going to be so we saw the case where a was 1, right? We saw the case where it was just x minus 1 squared in the denominator. So what is that going to give you? Well, you're going to have ax plus b to the negative 1. Then you're going to have a negative sign. And then you're also, just in case this number a was not 1, you would have to divide by it because of some chain rule that would go on. And by the way, if you when I say this stuff and I say you don't have to do the substitution, I just want to make it really clear that it's totally fine if you do the substitution. And also, if you're having trouble understanding why this is, the best way that you can understand why this is to take derivatives. So try an example. Try, pick a number for a and b, like try, 1 over 2x minus 3 or something squared, and check that if you use this formula, that when you take the derivative, you get the right thing. And I think that will really help you understand why this works the way it does. And that really goes for so many things in this class. I think one of the best ways you can understand how something works is to check it. So when you get an antiderivative, check it by taking the derivative, and that will go a long way in helping you understand why it's the antiderivative. And on that note, there's one other thing I should say, which is that you can check your answers for this, right? So we haven't been doing that mostly for the sake of time, but once you find what your numerators are, if you wanted to check whether they're correct, you could just take those two fractions, so in this case it's these fractions here, add them together and verify that you get this fraction, and you should. And I think that would also help if you're still kind of a little uncertain about like why this works or how it works. I think checking would really help you understand that process. All right, we're going to do one more example. So this example is going to kind of bring together basically what we saw in the last example, but also kind of make it a little bit trickier. So we have 4x squared plus 10x plus 12, all divided by x cubed plus 4x squared plus 4x dx. Okay, so the first thing we want to do is factor our denominator. So we can start by factoring out an x. So we have x squared plus 4x plus 4. And so how does that remaining part factor? Well, it factors as x plus 2 times x plus 2. So like in the previous example, we have a repeated factor. And so that tells us this is going to break down into the sum of 3 different fractions. So the first one we can say as a over x. The second one we can say as b over x plus 2. And then the third one is going to be c over x plus 2 squared. Okay, so now we want to make our common denominators as we did on some of the other examples. So we have a over x, so we want to multiply by whatever's missing, right? So for this first fraction, what are we missing? We're missing an x plus 2 squared. And then for the next fraction, we're missing an x and we're missing another x plus 2. And then for this last one, we're just missing an x. So again, to make this a little easier, let's just write down what these other fractions are going to equal. So x plus 2 squared, that's going to be x squared plus 4x plus 4. And then x times x plus 2 is going to be x squared plus 2x. Okay, so let's see what this gives us. So our first fraction is going to be ax squared plus 4ax plus 4a over our new denominator. And then our next fraction is going to be bx squared plus 2bx over x times x plus 2 squared. And then our third one is just going to be cx over x times x plus 2 squared. Okay, so again, we want to compare our new numerator. So our new numerator will be whatever we get by adding these 3 things together. We want to compare that to our initial numerator. So we have ax squared plus 4ax plus 4a plus bx squared plus 2bx plus cx. That is supposed to equal to 4x squared plus 10x plus 12. So again, just want to compare left and right hand side. So let's see, where are all the x squareds coming from? Well, we have an ax squared and we have a bx squared. And then on the right hand side, we have 4x squared. So that means that a plus b has to equal 4. And then if we look at the x's, so we have a 4ax, we have a 2bx, and we have a cx. And so that has to equal up to 10. So that tells us that 4a plus 2b plus c together has to equal 10. And then our final one, we have 4a is equal to 12. So again, it's a nice one where we'll be able to get one of our numerators right from that. So the first one we can figure out, as we just said, if 4a is equal to 12, that means that a has to be equal to 3. Okay, so now let's maybe take this second one, or sorry, the first one. This one's going to help us immediately as well, because now we know a plus, or sorry, other way around, 3 plus b is supposed to equal 4. And so that tells us that b has to equal 1. And so now to find what c is, we can just take this second equation and plug in what we found a and b to be. So we have 4 times 3 plus 2 times 1 plus c is supposed to equal 10. And so that tells us that we have 12 plus 2 plus c is going to equal 10. So c is going to be equal to 10 minus 14. So c is equal to -4. Okay, so now we're going to write down this integral. So our original integral was, again, 4x squared plus 10x plus 12, all divided by x cubed plus 4x squared plus 4x dx. And so we just figured out that this can be broken down into 3 fractions. So we found that a was equal to 3. And so remember, a was the numerator that went with just x. So we have 3 over x. And then for b, we found that b was equal to 1. And so that was the numerator that went with just x plus 2. So b over x plus 2. And then we found that c was -4. And that was the denominator, or the numerator that went with x plus 2 squared. Okay, so now we can pull out the coefficients. So we have 1 over x dx plus, this one is just the integral of 1 over x plus 2 dx. And then here we have -4 times the integral of 1 over x plus 2 squared dx. So we end up with 3 times ln of absolute value of x plus ln of absolute value of x plus 2 minus 4 times, so here we have x plus 2 to the -1 times -1 plus c. So altogether, this gives us 3 times ln of absolute value of x plus ln of absolute value of x plus 2 plus, and then we can write this as 4 over x plus 2 plus c. So yeah, sorry, this was probably kind of a longer video, but there's just a lot of, calculation that goes into this, a lot of just sort of algebra. So in the next video, we're going to see that there are some situations where the denominators are not linear. So far, right, we've seen all the denominators are just like things like ax plus b or maybe ax plus b squared. We'll see in the next video that you can also have denominators that are basically quadratics that cannot be factored. And in that case, the numerator has to be a little different. So we'll see how that goes. And then we'll also talk about how if you start with a fraction where the numerator has a bigger degree than the denominator, you have to, before you do partial fractions, you have to do polynomial long division. So I just want to give you a heads up that polynomial long division is something that is considered a prerequisite for this class. So I'm going to go through examples, but I'm not going to teach it from scratch. So hopefully you've learned polynomial long division. You should have learned it in a pre-calculus class at North, and maybe actually even in an algebra class at North. But if you haven't seen it, or if you're a little bit rusty on it, you should probably go seek out some videos. I'm sure there's plenty of YouTube videos out there. It's not very hard, but it's just something that you have to kind of do some practice to get comfortable with. So that's polynomial long division. We'll see that in the next video. All right, I will see you next time.